I hope you are not getting discouraged by the talk of uncertainty so much, but the fact is, when you have so much at stake in the future and big decisions are online, you better be aware of the uncertainty in the information, and that should not be misconstrued as lack of knowledge or and so on. It is just because we are dealing with a very nonlinear system with human anthroposphere, putting in much more nonlinearity into the Earth system. We have to be sure that we know what we are modeling and what are the uncertainties we are building in. So it's a good thing. It's a scientific thing. It's a reliable thing, and it's usable information. Decisions are made under uncertainty, so don't misconstrue this at all. Nonetheless, going on, the IPCC scenarios have evolved from the first assessment report with simple models, which got more complicated by using prescribed ice, land surface, and more on cloud physics. So the first assessment report, for example, had a swamp ocean. So it was not a dynamic ocean. It was like a slab, just taking up heat, transporting heat, and giving back heat. None of this wind-driven and thermohaline circulation and so on. Second assessment report added more radiative forcings like aerosols and volcanic activity. Oceans became more sophisticated, realistic. Third assessment report added more details like overturning circulation. Assessment report 4 was pretty close to an Earth system model with atmospheric chemistry, carbon cycle, interactive vegetation, and so on. And you can see that the resolution of the models got better. So you can see the representation of topography and the ocean, for example, get better as you improve resolution as well, which improves the physics. Orographic rain flows over topography in the ocean and associated mixing and density conversions and so on. So the solutions obviously get better as you improve resolutions. We have to know what the limit is, plus we have to know whether just increasing resolution is important or adding proper Earth system feedbacks is also critical. So that's a question that still is going to be improving over time. So looking again at hierarchy of models and uncertainties in input, forcing, parameterizations, and feedbacks. You have integrated assessment models which focus on these things we talked about: energy, health, economy, agriculture, forestry. Climate models have a lot of overlap with them in terms of agriculture, forestry, so dynamic vegetation, carbon cycle, water, ecosystems, cryosphere, and some parts of ocean in terms of fisheries, for example, or energy from the oceans, and so on. And impacts, adaptation, vulnerability models that we talked about have overlaps in terms of human settlements and infrastructure, sea level rise, impacts, and adaptation, vulnerability, and so on. And of course cryosphere, which also affects stream flows, agriculture, fisheries, certain communities like the Inuits, etc. Okay, so you can imagine that the uncertainties involved in the input, in the forcing, and the parameterizations and feedbacks are all different in these each of these models. If you think about top-down scenarios where impacts first approach, or a bottom-up vulnerability and threshold first approach in here, then the comparison of stages involved in identifying and evaluating adaptation options under climate change conditions can be different. So here you have climate models, scenarios, and impacts first approach. So you start with structure, impacts problem. So you begin with questions: what if climate extremes change according to scenarios X, Y, and Z? So we did RCPs and SSPs and looked at this already. Then you look at assessing relevant climatic changes from climate change models and downscaling for local impacts. So you start with climate change models, scenarios, impacts, assessments, reports, and you assess relevant impacts based on projected climate changes. Let me stop this here. My doorbell is so continuing the thought, I got cut off, so hopefully there is no discontinuity. We were looking at the top-down approach of climate models, scenarios, and impacts first. So we design and assess adaptation options for relevant impacts derived from these steps, and then evaluate the outcomes and feedback to the structure impact problem. So in the other approach, where vulnerability and thresholds first approach, the bottom-up approach, you begin with questions like: where are the sensitivities, thresholds, priorities considering climate variabilities? What can communities cope with? So you worry about the capacity, adaptation capacity, coping abilities, vulnerabilities of the communities that are being impacted. So you identify development context, hazards they are going to face from climate change, and their vulnerability problems. You identify vulnerabilities, sensitivities, and thresholds in the system in which they live, and then you propose adaptation measures based on that information, which is missing in this top-down approach. And the input climate change projections and other relevant information about underlying drivers is going to drive the assessment of adaptation measures and timing for action against climate change scenarios. So it's almost like a co-development of the adaptation options with climate change scenarios that are possible. Then you assess trade-offs between adaptation options and then evaluate outcomes, and then you go back to identifying the context again and looking at hazards, and metrics can be about reducing vulnerabilities, increasing resilience, reducing risk and exposure, and so on. Okay, so the additional uncertainties that remain in assessing the long-term impacts of anthropogenic climate change can be looked at this way. So again, looking at the chain of links: greenhouse gas emissions, greenhouse gas concentrations. We already talked about the uncertainties here in terms of carbon cycle modeling. Then you have non-greenhouse gas drivers of global and local climate change. We'll look at these in a bit more detail. These are very critical, which are not always considered in the Earth system models. So loss of conservation of physical quantities can happen when you do offline things like hydrology model. For example, if you run a hydrology model offline by forcing with the climate model output, it doesn't necessarily conserve water. Okay, that's just the reality of how these things work. Then you produce local climate change information. We will look at what bias correction means. That's a way to reduce the uncertainties in the model by using past data to even correct future projections. And look at biophysical impacts, interactions between biophysical impacts, and then come to social impacts. So the implication of uncertainty in emissions and concentrations becomes significant when you look at assessments over longer time frames. So all these things have to be kept in mind. It essentially comes down to whether you want to use the same model with various SSPs and RCPs, or you want to use multiple models for each set of SSPs and RSPs. The outcome is not necessarily the same. This is an example of the uncertainties introduced by in number of models giving increased runoff in the future. So the number of climate models under which an increase in runoff is projected for each land grid cell using runoff simulations from MacPDM hydrological model driven by IPCC AR4 climate model outputs. So when you do these offline models, you can see that there are a number of models giving increased runoff, there are a number of models giving decreased runoff, and so on. So these uncertainties were not thought of much when people were just doing hydrology for managing water resources and so on. But now when we are thinking about climate change and future projections, and you have to adapt and adjust to sustainably managing water resources in a warming world, then it becomes very critical that we know what we are doing when we do offline modeling versus online modeling. Online modeling is essentially when the hydrology model is within the Earth system model, so it's exchanging water with the atmosphere, receiving water with the atmosphere, doing runoff with the ocean, and there is a water balance that's dynamically and thermodynamically happening, especially when you also include the vegetation, evapotranspiration, and so on. But when you run offline, you are missing that full dynamic water balance. So we have to be very careful about these things in terms of uncertainties and biases.